All right, so let's continue with our discussion. And now I want to talk about one of the applications of these concepts, okay? And I'm going to give this slightly new topic name, okay? Let's call this the least squares method. And basically fitting a model quote unquote to data points. This model obviously is slightly different from our models in the control theoretical sense, like a transfer function or let's say a state space model or things like that. But you will see that it's also loosely related because there are applications of optimization where you actually fit actually a transfer function to your observed data. Okay, in that context it's called a system identification. In system identification you have a system which gives you a response to some specific signals, and you want to find the best fitting transfer function to that model. So that also can be formulated as an optimization problem. But for now, we are restricting ourselves to simpler problem. Okay. So consider the following problem, right? Where we actually, the model that we are talking about is basically a function, and data, what we call data, is actually a number of points in that functional space. Okay, so let me give you an example. Let's say that we basically have the X domain, and you have basically a number of points here. Let's say these are our data points, let's say at x1, x2, x3, x4. And we know that for those points, we have specific y points. So this is x, this is y. Okay, so I have a y1, and let's say I have at x2, I have a y2. Let's say at x3, I have, sorry, this became a, let's say that this is my y3, and finally, let's say at x4, I have again another y4. Okay, so I have a number of points, and my problem is to find the best fitting, let's say, line. We don't know how that line goes, but we can feel like it's somewhat going like this. Okay, so we know that this has a functional form. So this line, let's say best fitting line, which has a functional form that is essentially a function of x, but also a function of a number of unknown parameters. For a line, we know that we have two unknown parameters, alpha 1x plus alpha 2 with alpha 1, alpha 2 unknown. Okay, and the question, as I just said, is what is the best fitting line? In general, this is basically an arbitrary function of a number of parameters. Okay, so if a line given the xi, yi, I equals 1 to up to n data points. The the interesting thing that makes this problem actually the interesting thing that we want to study is actually what happens if you have many data points. Okay, as we will see, if you have the number of data points equal to the number of unknown variables, this is relatively simpler, and I'm going to give you an example in a minute. But it becomes more interesting when you have many data points, but just two variables to find out. Okay, let's say you are trying to find out, in this example, there are 4 data points, but we are trying to find a best fitting line. So most likely this line will not be able to pass from all the points, because we know that a line can only pass from uniquely from 2 points. The 2 points actually define the line, but there are more points. So what should we do with the other points? Okay. In that case, we come to the concept of the best fitting line. Okay. How to use all of the data points, but still be able to find the best fitting line. Okay. So in general, we have a function or an arbitrary function of a number of parameters. These are our alpha parameters, right? So instead of a line, you can have a quadratic function. Instead of a line, you can have another function which is parametric. Somehow it has a mathematical description, but it's not necessarily a line or necessarily a quadratic function. So in that case, you will have, again, number of data points like this, right? But then you will have, essentially, you will be looking at finding, let's say, a best fitting function like this, okay? So find the function parameters, okay? So if it's parametric, that means you know the structure. Like in this case, we know that this is our line formula, and we know that it's a line. Only alpha 1 and alpha 2 are unknown. You can also have here f of alpha 1, alpha n, and if this is x, also it's a function of x. Okay? So you are trying to find the alpha parameters, but you know the structure of f. Okay? In fact, a side note, if you don't know what the structure of f is, then this becomes, instead of an optimization problem, it becomes an optimal control problem. That means find the function rather than find the values of the parameters. Okay? Note, and I'm going to exemplify that in a minute, this problem is closely related with basic linear algebra. Linear algebra, where you have vectors and matrices, okay? So in the sense that if you consider a linear equation, A times alpha equals B, okay? So B is a vector, alpha is a vector, A is a matrix. So alpha is a vector of unknowns, okay? Unknown parameters. Alpha is in Rn, and A is an n by n invertible matrix. Okay, and B is also an n by 1 vector of constants. Okay, What happens in this case? Well, you do this, right? You find A inverse. Then you do this, right? You multiply both sides of the equation. Multiply both sides by A inverse, which gives you A inverse times A alpha is equal to A inverse times B. And A inverse and A become the identity matrix. Identity matrix times alpha becomes alpha. So alpha becomes simply A to the power minus 1 times B. And that actually solves your problem. So alpha unknowns determined. Okay, this is how we solve a linear system of equations, and I'm going to show you how that relates into our problem with an example. Okay, so example. Now this example is the simpler version of the problem that we have defined. Okay, it's still fitting a model to the data, but we have number of data points being equal to the number of unknown variables. Okay, so let's see how that goes. All right, so in this case, okay, you have the problem is actually very simple. And we know how to solve it simply by our previous knowledge, okay? But we have x1 and y1, the first point, and we have x2 and y2, the second point. And we know that only a single line can pass from this. So we have actually we also have a unique line. Okay, so we know that this line is a function of x, but it's also a function of the two parameters that are unknown at this point, alpha 1x plus alpha 2. So the question is, what are alpha 1 and alpha 2? Obviously, you can solve this problem without this formalism that we will talk about, but this can be generalized to functions that are not a line. For example, for a quadratic, if 3 points are given, you can uniquely find, in the same way that we will do right now, you can find that quadratic function that passes from that 3 points. Okay? So what's the key here is that the set of points xi, yi, I equals 1, 2, basically satisfies the parametric function. What does it mean to have a parametric function? This is a parametric function, right? This is a function of x, but it also has alpha 1 and alpha 2 as parameters. So it's a parametric function in terms of alpha 1 and alpha 2. So how do we solve that? Well, we basically impose that the fact that these 2 points have to satisfy the parametric form. So we construct those constraints. We know that y1 has to be equal to alpha 1 x1. So we put x1 in the parametric form, and we also put y1 in the parametric form, and we know that y1 has to be equal to alpha 1 x1 plus alpha 2. And also y2, it needs to also satisfy the second point also needs to satisfy the parametric form. So y2 needs to be equal to the same alpha 1 times, this time x2 plus alpha 2. Okay, so these two equations needs to be satisfied for this line. So if I put this in a vector matrix form, right, So I want to put this into A times alpha is equal to B form. Here alpha is just our two unknowns, alpha 1 and alpha 2. So let's construct this matrix over here, right? So we have alpha 1 and alpha 2 as our unknowns, and we have to have a B vector here. Take a look at the equations. Alpha 1 is multiplied by x1. So x1 multiplies alpha 1, and alpha 2 multiplies simply 1. And what is on the other side? You just have the data point, the y data point, y1. Similarly, in the second equation, right, alpha 1 multiplies x2, right, and alpha 2 multiplies 1, and you still have y2 over here. Okay, so you have this linear algebraic form that we just discussed a minute ago, and we know how to solve, right? We just need to take the inverse of the A matrix, and then we will just multiply it with the y vector in order to find alpha 1 and alpha 2. So let's try to do that. First of all, for A to be invertible, we need determinant of A being different from 0. Again, a linear algebraic condition. Okay, what is the determinant of A? Determinant of A is simply, you see, is equal to x1 minus x2. That needs to be different from 0. Now, if you look at this, this is a very meaningful condition, right? If x1 is equal to x2, you don't have 2 points, but you just have 1 point. And if you have 1 point, there is no way you can uniquely solve this problem. In fact, there are infinitely many lines passing from this single point. So in order to have a unique solution for alpha 1 and alpha 2, I need to have this condition satisfied. Okay? So what is unless x1 equals x2, right? So if that happens, you have a degenerate problem and you cannot find unique alpha 1 and alpha 2. But if that's the case, we can construct the inverse of A. And what is that? We know that this is 1 over the determinant of A times the adjoint of A. Please review again these concepts, right? So the determinant obviously is x1 minus x2. And the adjoint matrix is constructed from the original matrix. Over here, you just you consider this intersection and you take the determinant of the part that is remaining over here. So in this case, it's just a single number. Same goes with the diagonal entry at the bottom. So I consider this intersection and the remaining element here is x1. And for the remaining off diagonal entries, you have basically plus minus, right? You have this entry over here with a minus sign and this entry over here with a minus sign. Okay? So that is our inverse matrix. So hence, we have alpha 1 and alpha 2, the unknowns, being equal to a to the power minus 1 times the y matrices, y1 and y2. Okay, so what is that equal to? Well, that is equal to 1 over x1 minus x2, this matrix 1 minus 1 minus x2, x1 times y1 and y2, and that is equal to, let's keep the 1 over x1 minus x2 over here. Let's make the multiplication. This is 1 times y1 minus y2, so y1 minus y2 And in the second entry, you have minus y1 x2 plus x1 y2. Okay, so that becomes simply y1 minus y2 over x1 minus x2. Now you would notice that this is nothing but the slope of the line. Okay, so the difference of y divided by the difference of x is basically slope of this line, and the slope of the line is nothing but alpha 1, right? So you see that here we have the slope of the line emerging from this calculation. Similarly, over here you have simply x1 y2 minus x2 y1 over x1 minus x2. Okay, it's slightly more kind of difficult to see why, basically how this corresponds to the solution of the line, but I will show you with a simple example. Okay, so that's our alpha 1 and alpha 2, right? Alpha 1 and alpha 2. I will finish off this with a numerical example where everything is kind of obviously visible. Okay, so here's a line. So let's say that we have 1, 2, and 3 here, and we have 1 and 2 here. So let's say that we have a point over here at x is equal to 1 and y is equal to 2, and also we have a point over here where y is equal to 3 and x is equal to 2. So we have a line here. We know that this line will pass from here, okay, from 1. And we know that this 1 is where x is equal to 0, and that corresponds to our alpha 2. Okay, so let's make the calculation. So I have x1 equals 1, y1 equals 2, x2 equals 2, y2 equals 3. So our solution, right, alpha 1, alpha 2, by using this equation above, I will directly calculate it. Y1 minus y2, y1 minus y2, so it's 2 minus 3 over 1 minus 2. And over here we have, if you make the calculation, we have 3 minus 4 over 1 minus 2. Okay, so that gives us, this is minus 1 over minus 1, it is 1. This is minus 1 over minus 1, it's also 1. Okay, so our equation is simply, remember, alpha 1x plus alpha 2, and in our case this is 1 times x plus 1. Sorry, so okay, so the slope is 1, obviously, and also when we let x goes to 0, alpha 2 gives us 1, which is this point over here, right? This is our alpha 2. Okay, so that's an example on how when we have the number of data points equal to the number of unknowns, it becomes basically simply a matrix inversion problem. Okay, now what's happening in general, and which is up next for next week, okay, usually things get more complicated, where simply a times alpha equals b has no solution because we have too many equations. Okay, usually that's the cause. Too many equations means too many data points. Remember, if you're trying to fit a line and if there are 2 points, it's a simple problem. But if you have one too many, that means 3 or more, basically you cannot find a solution that is a line passing through all those points. So that means this equation A alpha equals B is actually without any solution. And the interesting extension is, how do we proceed if we have no solution? How can we find, in a sense, a best fitting line? Okay, so I'm going to break at this point for this week, and we will continue from here. All right.